Hi folks, today we're going to identify wholes of irrational functions. In the last set of notes we talked about the domain of rational functions and what x values you couldn't have in the domain because it would make the denominator of 0. We kind of have a similar idea today when we're identifying the wholes of rational functions. And what a whole is exactly what it sounds like. So we have a hyperbola for a rational function. And it looks like this. It's just a sketch. We have asymptotes along the line y equals 0 and x equals 0. But perhaps at some point in the hyperbola, we have this open spot. This open spot that doesn't have a value. It's almost as if somebody has taken that value, pinched it, and removed it from that graph. And so that is a whole. Now, a lot of times, you're not going to really see a whole, because a whole is one particular point that's removed from a graph. Now remember that a graph is made up of infinitely many points. So it's really not going to look like you have a whole here. It's just going to look like it just kind of continues. But you have to be able to pick out the wholes and the parts of the graph that are not defined. So let's talk about when you know that there is a hole in the graph. If there are common factors that are the same on the top of the rational function and the bottom of the rational function, if there are common factors, then there is a hole in the graph, and it's called a point of discontinuity. Discontinuity. So dis means not, continuity kind of means continuing, so it's a point of discontinuity. It's not completely continuing, it's got a hole right there. So in order to find the wholes of a rational function, remember the wholes are where there are common factors, so you're going to have to find all of the factors in the top and bottom. So factor the numerator and denominator completely. Identify and cancel factors that are shared by the numerator and the denominator. And once you cancel out those factors, set that common factor that you canceled out equal to 0. And solve. Find the x value for that common factor. Once you do that, because a whole is a point, it's an x and a y value, you'll get the x value when you set the common factor equal to 0, but then you have to substitute that x value of the whole into the simplified equation so that you can get the y value that goes along with it. And then you just write the whole as an ordered pair, x comma y. So it seems more complicated than it actually is. We have 3 problems to practice with today, and then there is an assignment. So it says find the domain of the following rational functions, and actually it should say find the wholes. Find the wholes of the following rational functions. I think when we created this, we just kind of reused all of that. So find the wholes of the following rational functions. So remember, wholes are where we have common factors. So in number 1, I have the top of x minus 3. That's already factored. It's linear. There's nothing else to do with it. But in the denominator, there's stuff to factor. So it's a trinomial. That means I'm going to use magic numbers. I need 2 numbers that multiply to give me 6, but they add to give me negative 5. So numbers that add to give me, or multiply to give me 6 would be 1 and 6 and 2 and 3. Either they both need to be positive or they both need to be negative. In this case, they both need to be negative because the sum is negative. So those 2 numbers are negative 2 and negative 3. That's my factored form of the denominator. So we factored. Now we want to identify and cancel factors that are shared in the numerator and the denominator. So I notice that x minus 3 appears in the top and the bottom. So I'm going to cancel those out. My function f of x gets simplified to a 1 because there's nothing else on top except for times 1 over x minus 2. That's my simplified function. But it just so happens that I canceled out factors. So there is a hole where x minus 3 equals 0. So I took this canceled factor, I set it equal to 0, and I need to solve. So we know that if my factor is x minus 3 equals 0, well then the x value is going to be equal to the opposite of minus 3. That's positive 3. So that happens to be the x value of the whole. So I'm going to go ahead and highlight this so you can kind of keep these pieces straight. That's the x value. But we need the ordered pair. We need the y value also. So we're going to take this x value and we're going to substitute it in our function. So instead of f of x equals 1 over x minus 2, we're going to say f of, what is the x value? Well, the x value is 3. So f of 3 equals 1 over 3 minus 2. And 3 minus 2 is 1. And 1 divided by 1 is 1. So what I'm finding here is the y value. The f of x value, or the y value, is 1. And that shows up right here as the y value of the whole. So if I were to graph this function, either on paper or on Desmos, I would need to realize that there is a hole, a missing value, kind of an open ghost of a point, shadow of a point that used to be there but isn't anymore, and it's at the point 3, 1. So that's the idea today, to find those holes in the functions. So I'm going to do the same thing with number 2. I'm going to factor the top and bottom so that I can see what factors get canceled out. So the numerator is x minus 2, it's already factored. The denominator is a trinomial. Two numbers that multiply to be 8 and add to be negative 6 would be 4 and 2, but they both need to be negative so that they can add to be negative 6. So negative 4 and negative 2. So think about think about factors that cancel. The factor x minus 2 is the same on top and bottom, so it will cancel. My function gets simplified to 1 over x minus 4. A 1 is on top because anything can be multiplied by 1. And if you get rid of everything on the top, well, you can't just leave it blank. So you need to have a 1. It's kind of like 1 times this factor. So the 1 is still there. So that's my simplified fraction. However, a hole appears when x minus 2 is equal to 0. So I'm going to set that canceled factor equal to 0. And my x value is the opposite of negative 2, that's positive 2. That's the x value of the whole. Well, how do you find the y value? If you have an equation and you have an x value, you can plug it in and you can get the y value. So I don't want f of x, I want f of 2. F of 2 equals 1 over 2 minus 4. 2 minus 4 is negative 2. So this is negative 1/2. The y value is negative 1/2. So my hole happens at 2, negative 1/2. There is a hole in the graph. Now in the last set of notes we talked about possible domains, and so I'm going to do this in a separate color, maybe pencil, maybe blue. I'll do it in blue. So in the last set of notes we talked about possible domains, and so this isn't really part of this set of notes, but I want to include this. The domain of this hyperbola is all real numbers, except x cannot be whatever makes the denominator 0. So here, x cannot be 2, and x also cannot be 4. Well, x can't be 2 because when x is 2, there's a hole there. But then x cannot be 4 either because chances are there's an asymptote there. So this kind of connects it to what we were doing when we found our domain of the rational functions. So number 3, let's try it out. There's nothing to factor in the numerator. We have x minus 4. This is a difference of 2 squares. So the square root of 16 is plus or minus 4. So I've got a plus 4 and an x minus 4. The x minus 4's cancel, so my simplified function is 1 over x plus 4. The hole occurs at that canceled factor when it equals 0, so x minus 4 equals 0. Gives me an x value of 4 for the hole. And that hole in the function I've got the x value for it, but I need to substitute it and get the y value. So I want f of 4 equals 1 over 4 plus 4, and that's 1 over 8. So the whole in the hyperbola happens at 4, 1/8. So now we've kind of learned that there are other things other than asymptotes that could create something that would affect the domain, something that x could not equal, and that happens to be a hole in the hyperbola, a hole in the graph. Basically a missing value, what used to be a point, and has now been removed.